The Lagrange point L1, a gravitational sweet spot. There exists a unique point in space known as the Lagrange point L1, where the gravitational forces of the Earth and the Sun perfectly balance each other. This equilibrium creates a stable environment ideal for placing telescopes and satellites. Located approximately 1.5 million kilometers from Earth towards the Sun, L1 allows for continuous observation of the cosmos without interruption. Here, objects can maintain their position with minimal fuel use, making it a fuel-efficient location for long-term missions. The SOHO spacecraft, or the Solar and Heliospheric Observatory, is stationed at L1, where it monitors the Sun 24/7. This vantage point enables scientists to predict solar flares and coronal mass ejections that could impact Earth. Another mission, DSCOVR, also resides at L1, watching for changes in space weather and Earth's energy balance. These missions benefit from the uninterrupted view that L1 provides, making it a crucial spot for solar monitoring and deep space observation. A day on Venus, longer than its year. Venus, often referred to as Earth's twin due to its similar size, has a unique rotation that sets it apart from other planets. A day on Venus lasts longer than its entire year. This is due to its extremely slow rotation, taking about 243 Earth days to complete one full spin on its axis, while it only takes about 225 Earth days to orbit the Sun. This means a day on Venus is longer than a year, a unique situation in the solar system. Adding to its uniqueness, Venus rotates in the opposite direction to most other planets, a movement known as retrograde rotation. If you were to stand on Venus, ignoring its hostile conditions, the Sun would appear to rise in the west and set in the east. This reverse rotation contributes to the length of its solar day, which is about 117 Earth days. The unusual rotation of Venus has significant consequences for its climate, creating a very slow atmospheric circulation near the surface, despite its upper atmosphere moving much faster. Saturn's floating potential. Saturn, the least dense planet in the solar system, has an average density of about 0.687 grams per cubic centimeter, less than the density of water, 1.0 grams per cubic centimeter. In theory, if you had a bathtub large enough, Saturn would float. This low density is due to its composition, primarily hydrogen and helium, both very light elements. Despite its massive volume, Saturn's density remains extremely low. Saturn's low density contributes to its fast rotation, completing a full rotation in just over 10.5 hours. This rapid spin causes the planet to bulge at the equator and flatten at the poles, making it the most visibly oblate planet in the solar system. Its rings, made of ice and rock, do not contribute much to its mass, but enhance its striking appearance. The concept of a floating planet is often used as a fun fact, but it is based on real physical properties that scientists use to understand a planet's internal structure, composition, and formation history. Jupiter's colossal storms. Jupiter's atmosphere is home to giant, long-lasting storms, the most famous being the Great Red Spot. This massive anticyclonic storm, located in Jupiter's southern hemisphere, is so large that 2 to 3 Earths could fit inside it. The Great Red Spot has been continuously observed since at least the 1600s, with wind speeds of over 400 kilometers per hour. Unlike Earth's storms, which are broken up by land, oceans, and changing temperatures, Jupiter's storms are sustained by its enormous internal heat and lack of a solid surface. The storm sits between two powerful jet streams that trap it in place, contributing to its stability and longevity. While it has shrunk in recent decades, it remains active, and scientists are not sure if it will fade completely or change form. The Juno spacecraft has provided valuable data, suggesting that the Great Red Spot may extend hundreds of kilometers into Jupiter's atmosphere. Hyperion's chaotic spin. Hyperion, one of Saturn's many moons, stands out due to its strange shape and unpredictable rotation. About 270 kilometers across, it looks like a giant, irregular sponge. Its low density and strange motion make it one of the most unusual bodies in the solar system. Hyperion's rotation is completely chaotic, meaning it doesn't spin in a steady or predictable way. Instead, its axis of rotation tumbles randomly as it orbits Saturn, a result of its irregular shape and gravitational interactions with nearby Titan, Saturn's largest moon. Hyperion's tumbling motion means there's no consistent day or night. Sunlight hits different parts unpredictably. Its density is very low, only about 0.55 grams per cubic centimeter, lower than water. This suggests it's made mostly of ice with a lot of empty space, explaining its porous surface. The Cassini mission confirmed this behavior, detecting signs that particles from Saturn's magnetic field interact with its surface, giving it a mild electrostatic environment. Pluto's hidden oceans. Despite being extremely far from the Sun, Pluto may still hold liquid water beneath its icy crust. Data from the New Horizons mission revealed surface features that suggest geological activity. Features like cracks, ridges, and resurfaced plains indicate movement below the surface, possibly caused by an internal ocean pushing against the crust. One key area of interest is Sputnik Planitia, a massive icy basin that appears to be sinking into Pluto's interior, suggesting a dense liquid layer beneath it. Models suggest that radioactive decay in Pluto's rocky core provides enough heat to keep water in a liquid state, insulated by thick layers of ice. This internal heat source, combined with insulation, prevents complete freezing. The ocean, if it exists, would be trapped under dozens or even hundreds of kilometers of ice and may contain salts, ammonia, or other antifreeze-like chemicals that lower the freezing point of water. Future missions could confirm its existence using seismology or radar mapping, providing direct clues about what lies below Pluto's frozen crust. Saturn's hexagonal North Pole. At Saturn's North Pole lies a gigantic hexagon-shaped jet stream that circles the pole continuously. This strange six-sided shape was first spotted by the Voyager spacecraft in the 1980s and later studied in detail by the Cassini mission. The hexagon is about 30,000 kilometers wide, larger than Earth, and is a stable and long-lasting feature in the planet's atmosphere. The hexagon is a cloud pattern, not a surface structure. It rotates with the planet and stays mostly in the same place, with winds inside moving at over 300 kilometers per hour. The reason for this hexagon isn't fully known, but it may result from fluid dynamics in Saturn's atmosphere, particularly how winds at different latitudes interact. Laboratory experiments with rotating fluids have created similar polygon shapes, supporting this idea. However, why Saturn's hexagon is so large and stable remains a mystery. Diamond rain on Uranus and Neptune. The atmospheres of Neptune and Uranus are rich in hydrocarbons like methane, which contains carbon. Deep inside these planets, pressures reach millions of times Earth's atmospheric pressure. At these depths, the pressure is so intense that it crushes carbon atoms into diamond. Scientists believe that under the right temperature and pressure, methane molecules break apart, and the carbon atoms reform as crystals of solid diamond. These diamonds then fall like rain through the planet's interior. The idea was first proposed in the 1970s, but gained more attention with lab experiments. Scientists simulated conditions similar to Neptune and Uranus using high-powered lasers, successfully creating diamond crystals by compressing hydrocarbons under extreme conditions. This diamond rain could contribute to heat and energy flow inside these ice giants, though the exact effects are still being studied. Venus's crushing atmosphere. Venus has one of the most extreme atmospheres in the solar system, made mostly of carbon dioxide with clouds of sulfuric acid. Its surface pressure is about 92 times higher than Earth's, equivalent to being almost a kilometer underwater on Earth. This crushing pressure, combined with intense heat about 465 degrees Celsius, makes it incredibly challenging for spacecraft to survive. Most landers last less than an hour, with the longest lasting about 2 hours. The thick atmosphere not only causes pressure problems but also blocks visible light, making it hard to see the surface from orbit. Radar mapping is needed to build images of Venus's terrain. Future missions like NASA's Veritas and Da Vinci plan to explore Venus more safely, with Da Vinci sending a probe that descends through the atmosphere, measuring temperature, pressure, and composition. These missions aim to provide critical data during the fall, even if the probe doesn't survive on the surface. Titan's methane cycle. Titan, Saturn's largest moon, has a surface covered with rivers, lakes, and even seas, but instead of water, they are made of liquid methane and ethane. At Titan's extremely low temperatures, methane behaves like water does on Earth, evaporating, forming clouds, and raining back down. This creates a full methane cycle, with seasons and changing weather patterns. Titan's surface temperature is around -179 degrees Celsius, making water as hard as rock and methane a flowing liquid. Its dense atmosphere, mostly nitrogen, is thicker than Earth's, creating weather, wind, and cloud formations. Radar images show lakes mostly near the poles, with one sea, Kraken Mare, being larger than the Great Lakes combined. Titan also has islands that may appear and disappear, possibly due to floating chunks of ice. Mercury's slow shrinkage. Mercury, the smallest planet in the solar system, is slowly shrinking over billions of years as its interior cools. The planet's core takes up most of its volume, and as it loses heat, it solidifies and shrinks. This causes the outer layers to wrinkle and fold, forming cliffs and ridges on the surface. These cliffs, called lobate scarps, can be hundreds of kilometers long and several kilometers high, visible from space. The shrinking is estimated to be around 7 kilometers in diameter over the planet's history, creating massive deformation on the surface. Mercury doesn't have tectonic plates like Earth, so this shrinking happens in a simpler, one-piece fashion. The core, which likely makes up 85% of the planet's radius, pulls the crust inward as it contracts, breaking the surface and forming large step-like structures. The surface remains visible for billions of years due to the lack of erosion or weather. The moons drift away from Earth. The Moon is increasing its distance from Earth by about 3.8 centimeters per year. This has been measured with high precision using laser reflectors left by Apollo missions. The reason is tidal interaction. Earth's gravity pulls on the Moon, and the Moon pulls back on Earth's oceans, creating tides. This tidal friction transfers rotational energy from Earth to the Moon, causing the Moon to speed up slightly in its orbit and move farther away. At the same time, Earth's rotation slows down gradually, making days on Earth longer over time. Hundreds of millions of years ago, Earth had shorter days and a closer Moon. During the age of the dinosaurs, a day lasted about 23 hours, and the Moon was much larger in the sky. If this trend continues, Earth's days will eventually reach over 25 hours in the distant future. Jupiter's magnetic influence. Jupiter has the strongest magnetic field of any planet in the solar system, about 20,000 times stronger than Earth's. This magnetic field traps charged particles from the solar wind and accelerates them, forming intense radiation belts around the planet. The radiation is powerful enough to damage spacecraft electronics. Jupiter's magnetic field extends far beyond the planet, forming a huge structure called the magnetosphere, which is millions of kilometers across. This magnetosphere reaches past some of Jupiter's moons, exposing them to radiation. Io, one of Jupiter's largest moons, generates an electric current as it moves through the magnetic field, creating auroras at Jupiter's poles and contributing to plasma clouds around the planet. Triton's retrograde orbit. Triton, the largest moon of Neptune, has a retrograde orbit, meaning it orbits in the opposite direction to Neptune's rotation. This unusual motion suggests that Triton was not formed around Neptune, but was captured by its gravity. Triton may have been part of a binary system that passed too close to Neptune, with one object being ejected and the other captured. This backward orbit creates tidal forces between Triton and Neptune, gradually shrinking Triton's orbit. One day, Triton may get so close to Neptune that it will be torn apart, forming a new ring system around the planet. Triton's surface is extremely cold, around -235 degrees Celsius, and covered with nitrogen ice. Despite the cold, it shows geological activity, with cryovolcanoes releasing icy material instead of lava. The asteroid belt's empty spaces. The asteroid belt, located between Mars and Jupiter, is often imagined as a crowded field of rocks, but in reality it is mostly empty space. The asteroids are separated by millions of kilometers, and collisions are rare. A spacecraft flying through the belt would most likely see nothing nearby. The total mass of all the asteroids combined is less than 5% of the Moon's mass, with the largest object, Ceres, being only about 950 kilometers in diameter. The belt didn't come from a destroyed planet. Instead, it's made of material that never formed a planet. Jupiter's gravity prevented the objects from sticking together, stirring up the region and causing collisions that broke larger objects into smaller pieces. This kept the belt in a fragmented state. Most asteroids are made of rock, metal, or carbon-rich compounds, and studying them helps scientists understand the early solar system's building blocks. The failed planet zone. Between the orbits of Mars and Jupiter lies a region known as the asteroid belt, sometimes referred to as a failed planet zone. Some scientists believe this area could have formed a planet early in the solar system's history, but Jupiter's strong gravitational influence disrupted the process. Instead of forming one large body, the material remained fragmented. The total mass of all the asteroids in the belt is very small, only a fraction of the Moon's mass. This suggests that most of the original material was either ejected or incorporated into other bodies. The belt contains various types of asteroids, including carbon-rich C-type, silicate S-type, and metal-rich M-type. These compositional differences show that material from different parts of the early solar system ended up here. Uranus's tilted moons. Uranus rotates on its side with an axial tilt of about 98 degrees, making it the only planet with such an extreme tilt. As a result, its moons orbit in the same tilted plane, following the planet's unusual orientation. The most accepted theory is that a massive collision knocked Uranus over in its early history. This tilt causes extreme seasonal changes that last over 20 years, with the planet's poles pointing nearly at the Sun during parts of its orbit. Uranus's moons, including Titania, Oberon, Ariel, Umbriel, and Miranda, are relatively small and icy, showing signs of past geological activity. Some have valleys, cliffs, and possible cryovolcanoes. The tilt affects how sunlight hits the moons during their orbits, causing long periods of darkness and light. Miranda, one of the smallest moons, has one of the weirdest surfaces in the solar system, with massive cliffs, jumbled terrains, and structures that don't match any known pattern. The solar system's galactic orbit. The solar system is not stationary. It orbits around the center of the Milky Way galaxy. This journey takes about 225 to 250 million years to complete, meaning the last time the solar system was in its current position, dinosaurs didn't exist. This orbit is called the galactic year. The Sun, along with its planets, moves at an average speed of about 828,000 kilometers per hour, but due to the galaxy's size, the journey is incredibly long. The Milky Way is about 100,000 light-years wide, and the solar system is located roughly 27,000 light-years from the center on one of the spiral arms. The orbit isn't a perfect circle, it's slightly elliptical and involves vertical motion where the solar system moves above and below the galactic plane. This oscillation may happen every 30 to 40 million years, and some studies suggest it could be linked to mass extinction cycles, though the evidence is not conclusive. Ceres bright salt patches. Ceres, the largest object in the asteroid belt and classified as a dwarf planet, has a diameter of about 950 kilometers and is mostly made of rock and ice. One of its most unusual features is the presence of bright white spots on its surface. These spots are highly reflective and clearly visible in spacecraft images. They are made of salt deposits, primarily sodium carbonate, concentrated in Ocata crater, a large impact basin. Scientists believe these salts were left behind by briny water that seeped up from below the surface. As the liquid evaporated, it left salt deposits behind. This process is similar to what happens in dry lake beds on Earth. The Dawn spacecraft studied Ceres in detail from 2015 to 2018, confirming that the bright material was not ice, but salt left by recent cryovolcanic activity. This suggests that Ceres may still have some internal heat, with upwelling brine occurring within the last few million years. Moons outnumber planets. The solar system has 8 planets but more than 290 confirmed moons orbiting planets. Some gas giants like Jupiter and Saturn each have over 90 moons. These moons come in various sizes and types, with some being small and irregular, while others are larger than Mercury. Many are geologically inactive, but a few show remarkable activity. Io, a moon of Jupiter, is the most volcanically active body in the solar system, with hundreds of volcanoes that erupt constantly. Europa, another moon of Jupiter, has a smooth, icy surface and likely an ocean of liquid water beneath it. Enceladus, a moon of Saturn, has water geysers that eject material from cracks in its icy surface, creating a plume that extends into space. Titan, Saturn's largest moon, has rivers, lakes and seas of liquid methane, with a dense atmosphere that allows for weather systems and seasonal changes. Earth's Trojan asteroids. Earth shares its orbit with Trojan asteroids that travel with us, unseen to the naked eye. Trojan asteroids are small bodies that share a planet's orbit around the Sun, staying in stable gravitational zones called Lagrange points, specifically L4 and L5. These points are located 60 degrees ahead and behind the planet in its orbit. Earth has several known Trojan asteroids in these positions, which are hard to see due to their position relative to the Sun. The first Earth Trojan was discovered in 2010 and named 2010 TK7. It is about 300 meters in diameter and orbits near Earth's L4 point, moving in a tadpole-shaped path around the stable point. Trojan asteroids are also found around Jupiter, Neptune and Mars, with Jupiter having the most, over 10,000 known Trojans. These objects are stable over millions of years and provide valuable information about solar system formation. Long-period comets. Some comets take millennia to return, originating from the Oort cloud, a distant region that surrounds the solar system. This cloud may extend up to 100,000 astronomical units from the Sun. Comets from this area take thousands or even millions of years to complete one orbit, with highly elongated paths. Many only pass near the Sun once in recorded history. The Oort cloud has never been directly observed. Its existence is inferred from the orbits of long-period comets. These objects often appear suddenly and have no known source within the inner solar system. Their arrival angles suggest a spherical cloud of icy bodies far beyond Pluto, considered the outermost region of the solar system. When a comet from the Oort cloud is disturbed by nearby stars, gravity from the Milky Way, or internal shifts. It may fall toward the Sun. As it approaches, solar heat causes its ice to vaporize, forming a visible coma and tail. Solar wind and Earth's magnetosphere. The solar wind, a constant flow of charged particles released by the Sun, travels through space at speeds of up to 800 kilometers per second. When these particles reach Earth, they interact with our magnetosphere, the magnetic field that surrounds the planet. This interaction causes the magnetosphere to stretch and change shape, compressing it on the side facing the Sun and extending it into a long tail that reaches millions of kilometers into space. The solar wind is not constant. It can become much stronger during solar storms or coronal mass ejections, CMEs. These events release enormous bursts of solar material that can cause geomagnetic storms when they hit Earth's magnetic field. These storms affect satellites, communications, and power grids. The auroras, or northern and southern lights, are caused by solar wind particles entering Earth's upper atmosphere and colliding with gas molecules, releasing energy in the form of light. The heliosphere, the Sun's protective bubble. The heliosphere is a vast region of space influenced by the solar wind and the Sun's magnetic field, forming a protective bubble around the solar system. Inside this bubble, solar wind particles dominate, while outside, space is filled with galactic cosmic rays and particles from other stars. The heliosphere acts as a shield, blocking or deflecting some of this external radiation and protecting the planets from the full intensity of cosmic rays. The boundary of the heliosphere is called the heliopause, where the solar wind slows down and can no longer push back against interstellar particles. Beyond the heliopause lies interstellar space. The Voyager 1 and 2 spacecraft have both crossed this boundary, providing direct data. The shape of the heliosphere is not a perfect sphere. It's distorted by the movement of the solar system through the galaxy, forming a comet-like shape with a rounded front and a trailing tail. Uranus, the darkest planet. Uranus is one of the least reflective planets in the solar system, with an albedo of around 0.3, meaning it reflects only about 30% of the sunlight it receives. This makes it the darkest of the major planets in terms of visible reflectivity. The reason for this low reflectivity is still not fully understood, but scientists believe it may be due to a thick haze layer in the planet's upper atmosphere that absorbs sunlight instead of reflecting it. Uranus's atmosphere is composed mainly of hydrogen, helium, and methane. Methane absorbs red light and reflects blue, explaining the planet's pale blue-green color. However, a layer of haze particles seems to cover the methane clouds, reducing the amount of light that escapes and contributing to the planet's darker appearance. Observations from telescopes and spacecraft have shown that Uranus has very few visible cloud features compared to Jupiter and Saturn, making it appear flat and bland in most wavelengths. Venus's retrograde rotation. Venus has a retrograde rotation, meaning it spins from east to west, opposite to most other planets. It also rotates very slowly, with one full spin taking about 243 Earth days, longer than a Venusian year, which is about 225 Earth days. This backward rotation is unusual in the solar system, with only Venus and Uranus rotating in this direction. Scientists are still unsure what caused this reversal of spin. One leading theory is that Venus may have experienced a massive collision with another body early in its history, flipping its rotation or altering its spin direction over time. Another possibility is that gravitational interactions with the Sun and other planets gradually changed its rotation. Tidal forces from the Sun may have also influenced the spin, as Venus has a dense atmosphere that allows the Sun's gravity to interact with it more than with planets with thinner atmospheres. Mars's long seasons. Mars experiences 4 distinct seasons, just like Earth: spring, summer, autumn, and winter. These seasons are caused by the planet's axial tilt, which is about 25 degrees, very close to Earth's 23.5 degrees. However, a year on Mars lasts about 687 Earth days, meaning each season on Mars is roughly twice as long as a season on Earth. Mars's orbit is also more elliptical than Earth's, causing the seasons to be uneven in length. Northern summer is longer and milder, while southern summer is shorter and hotter. During winter, carbon dioxide from the atmosphere freezes and forms polar ice caps, which sublimate back into gas in summer, increasing atmospheric pressure. This seasonal cycling contributes to dust storms, cloud formation, and shifting winds. The Moon's stabilizing effect on Earth's tilt. Earth's axial tilt of about 23.5 degrees, which causes the changing of seasons, is stabilized largely due to the gravitational pull of the Moon. Without the Moon, Earth's tilt would vary much more over time, potentially reaching up to 60 degrees according to some models. This would cause extreme climate swings. The Moon's stabilizing effect comes from tidal forces. As Earth spins, the Moon's gravity pulls on the planet's equator, creating a torque that helps resist the chaotic influence of the Sun and other planets. This keeps Earth's axial tilt within a narrow range over long time periods. The tilt directly affects how much sunlight different parts of Earth receive during the year. If the tilt shifted too much, areas near the poles could become tropical, or equatorial regions could freeze, making long-term climate patterns unpredictable. Jupiter's cosmic shield. Jupiter, the largest planet in the solar system, plays a protective role by deflecting dangerous comets and asteroids. Its immense gravity can capture, redirect, or eject objects that enter the inner solar system, acting as a kind of gravitational shield for Earth and the other inner planets. Jupiter's gravity is strong enough to alter the trajectories of many incoming objects, with some being flung into space while others are pulled into Jupiter itself. Recorded impacts, such as comet Shoemaker-Levy 9 in 1994, show that Jupiter absorbs objects that might otherwise head toward Earth. Its presence reduces the number of potentially hazardous impacts, though it doesn't stop all threats. Uranus and Neptune. The ice giants. Uranus and Neptune, known as the ice giants, are composed of more ices like water, methane and ammonia in their interiors, unlike Jupiter and Saturn, which are mostly hydrogen and helium. Despite their size and importance, they are poorly explored, with only one spacecraft, Voyager 2, having flown past them in 1986 and 1989, respectively. Uranus has a strange rotation tilted at about 98 degrees, possibly due to a past collision. Its magnetic field is also highly tilted and off-center. Neptune has a more normal tilt, but an even more dynamic atmosphere, including storms, and winds up to 2,000 kilometers per hour, the fastest in the solar system. Both planets have faint ring systems, multiple moons, and complex weather patterns, but their deeper layers remain a mystery. Mercury's extreme temperatures. Mercury, the closest planet to the Sun, experiences extreme temperature swings due to its lack of atmosphere. Surface temperatures can reach plus 430 degrees C during the day, hot enough to melt some metals, and drop to around minus 70 degrees Celsius at night, colder than any temperature on Earth. This is one of the widest temperature ranges in the solar system. Mercury has only a thin exosphere made of atoms blasted off its surface by solar wind and micrometeoroids. It doesn't retain heat like Earth or Venus. Once the Sun sets, the heat escapes into space rapidly. The planet's slow rotation makes this effect more extreme, with each side of the planet exposed to long periods of heating or cooling. Zodiacal light, sunlight on interplanetary dust. Zodiacal light is a dim, diffuse glow visible in the night sky just before dawn or after sunset, appearing along the ecliptic, the path the Sun and planets follow. This glow is caused by sunlight reflecting off tiny dust particles in space, forming a cloud known as the interplanetary dust cloud. The dust comes from comets and asteroid collisions, spreading out along their orbits. Zodiacal light is easiest to see in areas with very dark skies and minimal light pollution, particularly near the equator during the spring and autumn months. The light looks like a soft triangular glow rising from the horizon. The dust particles responsible are very small, often less than a millimeter in size, but there are trillions of them, enough to reflect sunlight collectively. The Sun's dominant mass. The Sun contains over 99% of all the mass in the solar system, with approximately 99.86% of the total mass. All the planets, moons, asteroids and comets combined make up less than 0.2%. The Sun's gravity dominates the system, keeping all planets in orbit and defining the structure, dynamics and behavior of the entire system. The Sun's mass is about 1.989 quaternions 10 circumflex 30 kg. In comparison, Jupiter, the most massive planet, is only about 0.1% of that, while Earth is less than 0.003% of the Sun's mass. This difference shows how much the Sun controls the solar system. The Sun's mass also shapes the curvature of space-time in its vicinity, according to general relativity. Earth's magnetic field reversals. Earth's magnetic field has flipped polarity many times over millions of years, with the north and south magnetic poles switching places. These events, called geomagnetic reversals, are detected by studying magnetic patterns in ancient volcanic and sedimentary rocks. The last major reversal happened about 780,000 years ago, known as the Brunhes-Matuyama reversal. The magnetic field is generated by liquid iron moving in Earth's outer core, creating electric currents that produce the magnetic field. Over time, changes in the flow can lead to weakening, instability, and eventually pole reversal. These changes don't follow a set pattern, with the time between reversals varying from tens of thousands to millions of years. Europa's subsurface ocean. Europa, one of Jupiter's largest moons, is covered by a thick layer of ice beneath which scientists believe there is a liquid water ocean. The ocean may be 100 kilometers deep, far deeper than any on Earth, making Europa a key target in the search for extraterrestrial life. The subsurface ocean is kept warm by tidal heating, caused by Europa's elliptical orbit around Jupiter. The planet's strong gravity stretches and compresses Europa, creating internal friction that generates heat. Cracks and ridges on Europa's surface suggest that the ice moves and shifts, with some regions showing evidence of ice tectonics or convection. Plumes of water vapor have been detected erupting from Europa's surface, possibly originating from the subsurface ocean. If confirmed, these plumes offer a way to sample the ocean without drilling. NASA's Europa Clipper mission, launching in the 2020s, will study this possibility in detail. Saturn's rings, a temporary feature. Saturn's rings are one of the most iconic features in the solar system, composed mostly of ice particles, along with some rocky debris and dust. The particles range in size from tiny grains to chunks, several meters wide. Despite their massive appearance, the rings are very thin, usually only about 10 to 100 meters thick. The total mass of the rings is estimated to be only a fraction of a moon's mass. The rings are divided into sections labeled A, B, C, and so on, with gaps and divisions often shaped by small moons called shepherd moons. These moons influence the particles and keep ring edges sharp. The rings are not solid but dynamic systems made of countless orbiting pieces. Data from the Cassini spacecraft showed that the rings are losing material due to micrometeoroids and solar radiation, causing particles to fall into Saturn's atmosphere. This process, known as ring rain, is gradually depleting the rings over time. Estimates suggest that the rings could disappear in 100 to 300 million years. Sunlight's 8-minute journey to Earth. Light and other forms of electromagnetic radiation from the sun travel at a speed of approximately 299,792 kilometers per second, the speed of light. The average distance from the sun to Earth is about 150 million kilometers, meaning it takes sunlight around 8 minutes and 20 seconds to reach our planet. This delay means we always see the sun as it was 8 minutes ago. This time lag affects our real-time understanding of solar events. Solar observatories must account for this delay when monitoring changes on the sun's surface. The energy we receive on Earth is part of the electromagnetic spectrum, including visible light, ultraviolet radiation, and infrared radiation. All of these components travel at the same speed and take roughly the same time to arrive. The sun's core, the hottest place in the solar system. The sun's core is the hottest known region in the solar system, with temperatures reaching around 15 million degrees Celsius. This intense heat is produced by nuclear fusion, the process that powers the sun. In the core, hydrogen atoms are fused into helium, releasing massive amounts of energy according to Einstein's equation, E equals sin mc. 2. Loss. Every second, the sun converts about 600 million tons of hydrogen into helium, releasing vast amounts of light and heat. Most of this energy eventually reaches Earth as sunlight. The core is located in the innermost 25% of the sun's radius, with the radiative zone and convective zone above it. Energy produced in the core takes thousands to millions of years to reach the surface, after which it takes just 8 minutes to reach Earth. The heliosphere's boundary. The heliopause. The heliosphere forms a giant plasma bubble around the solar system, with the heliopause marking its outer boundary. Beyond the heliopause lies interstellar space, where particles and radiation come from other stars. The heliopause is the point where the pressure from the solar wind is balanced by that of the interstellar medium. Inside the heliosphere, the solar wind flows outward in all directions, slowing down at the termination shock, where it drops below supersonic speeds. Between the termination shock and the heliopause is the heliosheath, a turbulent region of slowed, compressed plasma. The Voyager 1 and 2 spacecraft crossed the heliopause in 2012 and 2018 respectively, providing direct data about conditions at the edge of the sun's influence. The solar cycle's influence on Earth's climate. The solar cycle is an 11-year pattern of activity that affects the number of sunspots, solar flares, and solar radiation. During solar maximum, the sun has more sunspots and emits more ultraviolet and X-ray radiation. During solar minimum, it's calmer with fewer active regions. These changes affect Earth's upper atmosphere and magnetic environment. Solar activity influences space weather, which can affect satellites, GPS, and power grids. Some studies suggest that solar cycles may slightly influence global temperatures, though the effect is small compared to greenhouse gases. Understanding the connection is important for climate modeling. Sunspots are darker, cooler regions caused by intense magnetic fields. More sunspots mean higher total solar output because the surrounding regions are brighter. Meteorites. Clues to the solar system's origin. Meteorites are pieces of rock or metal that survive their fall through Earth's atmosphere and land on the surface. Most come from the asteroid belt, with a few originating from the Moon or Mars. These space rocks are important because they often contain material unchanged for billions of years, acting as time capsules from the early solar system. Some meteorites are older than any rocks on Earth, with their chemical makeup revealing conditions from over 4.5 billion years ago when the sun and planets were forming. They often contain chondrules, round particles formed by rapid melting and cooling. By studying isotopes in meteorites, scientists can learn about radioactive decay, solar wind exposure, and early planet formation. Gas giants' rocky cores. Gas giants like Jupiter, Saturn, Uranus and Neptune have solid or rocky cores at their centers, surrounded by dense layers of gas. These cores formed early, attracting large amounts of gas from the protoplanetary disk. The cores of gas giants are composed of rock, metal, and ices depending on the planet. Jupiter and Saturn likely have solid cores that are 5 to 15 times the mass of Earth, surrounded by metallic hydrogen, a phase of hydrogen that acts like a metal under extreme pressure. This layer conducts electricity and contributes to planetary magnetic fields. Uranus and Neptune have smaller gaseous envelopes and larger cores rich in water, ammonia, and methane ices. Their interiors are less dominated by hydrogen and helium and more by volatile materials. Moons turning into rings. Moons that orbit too close to a planet can be destroyed by tidal forces caused by the planet's gravity. If a moon crosses the Roche limit, the gravitational pull can tear it apart and the debris can form a ring system around the planet. The Roche limit depends on the planet's size, mass, and the density of the satellite. Saturn's rings may have originated this way, with a former moon coming too close and being destroyed. The material stayed trapped in orbit, eventually forming the wide ring system we see today. Other planets like Uranus and Neptune might also have rings formed from broken moons. Jupiter's rings are faint and made mostly of dust, likely from small moons struck by micrometeoroids. The moon's volcanic past. The moon was volcanically active in its early history, with evidence of volcanic eruptions occurring between 4 and 1 billion years ago. These eruptions released lava that filled large impact basins, creating the dark regions known as Luna Maria. The smooth, flat appearance of these areas confirms past volcanic activity. The Luna Maria are mostly found on the near side of the moon, covering about 16% of the lunar surface and rich in basalt, a type of volcanic rock. These regions formed when magma rose from the moon's interior through cracks in the crust. The lava spread and cooled, forming large dark plains. Unlike Earth, the moon doesn't have plate tectonics. Its volcanic activity was mostly driven by internal heat left over from formation and by radioactive decay. Pluto's seasonal atmosphere. Pluto's orbit is highly elliptical, meaning its distance from the Sun changes significantly over time. When it gets closer to the Sun, its surface ices warm and sublimate, turning directly into gas. This process creates a temporary atmosphere mostly made of nitrogen, with some methane and carbon monoxide. As Pluto moves farther from the Sun, temperatures drop, and the gases in the atmosphere refreeze and settle back onto the surface as frost. This cycle of freezing and sublimation creates seasonal changes in atmospheric pressure and thickness. The atmosphere can nearly vanish at Pluto's farthest point. Pluto takes about 248 Earth years to complete one orbit, with seasons lasting for decades. Sun-grazing comets. Some comets, called sun-grazers, follow orbits that take them extremely close to the Sun. These objects often belong to the Kreutz family, a group of comets thought to be fragments of a larger one that broke apart centuries ago. As they approach the Sun, they are subjected to extreme heat and tidal forces, and most don't survive the journey. Sun-grazers can heat up to thousands of degrees Celsius near the Sun's surface. Their ices and volatile compounds rapidly turn into gas and plasma, creating bright tails before disintegration. Space-based solar observatories like SOHO and STEREO have captured hundreds of these events, helping track sun-grazers as they approach the Sun and often catch them vanishing in real time. Jupiter's differential rotation. Jupiter's equator spins faster than its poles, a phenomenon called differential rotation. Jupiter is not a solid planet, but is made mostly of gas and liquid, allowing different parts to rotate at different speeds. At Jupiter's equator, the atmosphere completes a rotation about 5 minutes faster than at the poles. This differential rotation drives the formation of Jupiter's bands, zones, and storms, creating massive jet streams that circle the planet in alternating directions. These winds reach speeds of up to 400 kilometers per hour, giving Jupiter its striped appearance. The Great Red Spot, a massive storm that has lasted for centuries, is powered by the shear between different rotating layers. Earth's temporary mini-moons. Earth occasionally captures small asteroids or rocks that enter its gravity well, temporarily becoming satellites known as temporarily captured orbiters or mini-moons. These objects typically stay in orbit for a few months to a few years before escaping or falling to Earth. They are very small, usually just 1 to 10 meters in diameter, making them hard to detect. One confirmed example is 2006 RH-120, a mini-moon that orbited Earth for about 11 months before leaving in 2007. These temporary satellites offer a chance to study small asteroids up close and could be targeted for exploration or sample return missions. Improved sky surveys and telescope networks may help spot more of them in the future. Mercury's aurorae-like emissions. Mercury does not have a thick atmosphere like Earth, but it still shows aurora-like activity due to its magnetic field interacting with charged particles from the Sun. These interactions cause energetic events on the surface, especially near the magnetic poles. While not true auroras like Earth's, the process is similar in principle. Mercury's magnetic field is about 100 times weaker than Earth's, but is still strong enough to create magnetospheric boundaries that guide solar wind particles toward the surface, especially near the poles. The result is a type of precipitation of particles that can be detected by scientific instruments. The Messenger spacecraft, which orbited Mercury between 2011 and 2015, made several discoveries about these interactions, finding evidence of flux transfer events and local changes in surface radiation. The solar system's dynamic environment. The solar system is a dynamic and ever-changing environment, with planets, moons, and other celestial bodies interacting in complex ways. From the gravitational dance of moons and planets to the extreme conditions found on distant worlds, each part of the solar system offers unique insights into the workings of the universe. As we continue to explore and study these celestial bodies, we gain a deeper understanding of our place in the cosmos and the processes that have shaped our solar system over billions of years.